Right, we are discussing other solutions other than Schwarzschild, which are spherically symmetric. So I have been talking a bit about the Kotler solution, the Schwarzschild solution with a cosmological constant. And the only other example I want to do in this section is the Reisner-Nordström matrix. That's a charged version of Schwarzschild. I think it's 5.2. And I will do this comparatively brief, so I will concentrate on things which are actually different from, we will look in particular at Reisner-Nordström black holes. Of course, it also describes regular bodies, the gravitational field outside of regular bodies. So the Reisner-Nordström solution is a version of Schwarzschild where you have in addition an electric charge, or if you like also magnetic charge, if you believe in magnetic monopoles. Now, if you think of astronomical applications, then most people would say charged stars, that's not really relevant. Yeah? If you look at the net charge of stars or any other celestial bodies, then it's very, very close to zero. So one usually thinks that the charge plays no important role for stars or other objects, other astrophysical objects. But nonetheless, I think it's interesting to see how a charge would change the picture qualitatively. We have seen how the gravitational constant changed the picture qualitatively, and also the charge will do this. So I will proceed in the same way as I did for Kotler. I will not derive the solution, I will just write it down. I think it should be clear what you have to do if you want to derive the Reisner-Nordström solution. You have to write down again the ansatz that your metric should be spherically symmetric and static. Actually, you can prove that it must be static under certain assumptions, but to simplify things, assume that it is static. And then you feed it into the field equation. And in this case, of course, it's a field equation with an electromagnetic field as a source. So on the right-hand side, you have the energy-momentum tensor of the electromagnetic field. We have been briefly talking about this. And then what you have to solve is a coupled system, Einstein's equations plus Maxwell's equation. And what you get for a solution is a metric and an electromagnetic field. And well, it's a coupled system of differential equations, so it takes some time actually to go through all the details, and I will certainly not do this here, because as I said, the solution is not to be thought to be of very big relevance. So I think I concentrate then on the Kerr spacetime, which will come later. So I just write down the metric. So what you get as a result from this solution is a metric which involves two parameters. Actually, this should not come as a surprise. For Schwarzschild, we had only one, which was associated with a mass. Obviously, now we will have a second one, which will be associated with a charge. Yeah? And the one associated with the mass is Rs. We know this already. And the new one, it's also of the dimension of a radius, so I call it Rq. And that's a radius which is associated with a charge. And the structure is exactly the same as Schwarzschild, so you have the same function now in the denominator under the dr squared. And you have the angular part, which I just abbreviate in this way. So that's the Reisner-Nordström solution. It was found by Hans Reisner in 1916 and by Gunnar Nordström, Finnish relativist, 2 years later. For some strange reason, in this case, everybody calls it the Reisner-Nordström solution. Yeah? If you compare it with Schwarzschild, it was found by Schwarzschild, and a few weeks later by Droste. But nobody calls it Schwarzschild-Droste solution. Yeah? In this case, one calls it Reisner-Nordström solution. So Nordström was 2 years later. And actually, Weil was in between. Weil found it in 1917. This was 1918. Reisner is an interesting person. He's an unusual suspect for doing work of this sort because he was an engineer. And he is best known for constructing an airplane which is named after him. One of these early airplanes. These things where just one person could sit in and without a hood on top and things like that. So it is named after a bird. I'm not quite sure. I think it is called Reisner Taube in German, Reisner Dove, but maybe I'm wrong. In any case, it's a bird. So that's the same person. It's the same Reisner. So for some reason, he was also interested in relativity, and he wrote this one paper on relativity theory. So if we look at the metric, we see that it is also asymptotically flat, just as a Schwarzschild metric, because if you send R to infinity, then this goes to 0, this goes to 0, and in the limit you get the flat metric, the Minkowski metric. So it's asymptotically flat. It is spherically symmetric. Spherically symmetric. It is static. And it's asymptotically flat. And actually you can prove that it is the only solution to Einstein's field equation coupled to an electromagnetic field with these properties. So it gives a unique field of a spherically symmetric charged body which is isolated from all other bodies. Okay, so if you approach R equal infinity, then you see that this term will die down stronger than this here. So if you are far away, but not yet at infinity, then this term can be neglected in comparison to this here, and then you have Schwarzschild. Yeah? So in leading order, if you are far away, and now you come in and look order by order when for terms of the gravitational field, the first term which you will be able to realize is just the usual Schwarzschild term. And for this reason, the RS can be interpreted in exactly the same way as for Schwarzschild. Yeah? Remember how we proceeded when identifying RS with a mass times some constants. We use a Newtonian limit, which is a good approximation far away from the body. And if you are so far away that this term is much smaller than this here, then the argument is still valid. So we have two constants of motion. Two constants in the metric. So it's a two-parameter family of solutions, and RS can be interpreted in exactly the same way as before by comparison with a Newtonian limit. And then we have a second one, and of course you would compare this by looking at the electromagnetic field which is associated with that. So I said what you have to solve is Einstein's equation coupled to Maxwell's equation. So you also get a solution to Maxwell's equation. And from the equation of Maxwell's equation, you can read off the charge. Just consider a sphere, look at the flow, at the flux through this sphere, and this gives you 4 pi r squared times the charge. And then you can identify the charge. And what you get is, with some funny constants, if you use a modern system of units, that RQ squared, RQ is a length, right? You can read it from this expression. RQ must be a length. And it is in the legal units which we have to use nowadays. It is g, gravitational constant, times the charge of your central object, 4 pi epsilon naught c to the 4. So essentially, this term here is a charge squared, and essentially this term here is a mass. Yeah? So these are the two parameters in the game. And now you see, when we discussed the lambda term, we had here a term lambda times r squared. So r squared was in the numerator. This means that the lambda term becomes relevant for big radii. Yeah, it modifies the metric at big radii. There the lambda term dominates over the mass term. Here you have a 1 over r squared. So the charge term is relevant close to the center, yeah, if r is small. So this modification of the metric will be relevant if you are close to the singularity. It will not change the picture much if you are far away from the object. So for a distance observer, the difference between Schwarzschild and Reisa-Nordström is not very big. But if you are, if you are adventurous enough to come close to the singularity, then you will see big differences. And actually, we will discuss this very soon. So that's an important thing which you should have in mind from the very beginning. The influence of the charge becomes relevant close to the singularity. And it still is a singularity because still we have here an r in the denominator, right? And now even squared. So the singularity at r equals 0 becomes even worse if this term is present. Yeah? So the curvature singularity will become even stronger. But yeah, so it will certainly still be a curvature singularity. But the question is, what happens to the horizons? The horizons are given by the zeros of this expression. And that's what we will discuss first. And then we will see that actually there's an interesting qualitative change, because now we have two horizons for a black hole in general. So where are the horizons? Horizons are determined by by the fact that this here becomes 0. Let me abbreviate this by f of r. So this is just this expression here, 1 minus rs over r plus rq squared over r squared. And if this is 0, if this has a 0 somewhere, then there is a horizon. So that's a quadratic equation, right? If I multiply it with r squared, then I get r squared minus rsr minus rq squared is 0. So this gives me the horizon. And everybody knows how to solve a quadratic equation. There's a standard formula, and the solution in this case is r plus minus is 1/2 of this is rs half plus minus root rs squared over 4. There's a sign wrong. There's a sign wrong. Just a writing mistake. It's plus rq squared, and that's important because now it becomes minus rq squared. And now you see there are two cases to be distinguished, namely, if this is positive, what we have under the square root, then we indeed get real solutions. But if this is negative, then this gives two complex solutions, and they have nothing to do with radial coordinates. Yeah? So we have to distinguish the following cases. So case 1 is, Case 1 is that this here is bigger than 0. This means the mass term dominates the charge term. And as I said, for all celestial bodies, stars, planets, or whatever, this is satisfied even with a much bigger sign here instead of just mere inequality. So what do we have then? Then we have two real solutions. Actually, both of them are positive. You see, if I use a plus sign, then obviously I have rs half plus rs half, which is positive. If I use a minus sign, I have to subtract here something which is smaller than rs half. Yeah, because here I have a minus a square. So what I subtract here is smaller than rs half, so also the second solution is positive. Yeah, we have two positive real solutions, so we have two horizons at r plus and r minus, which are given by these expressions here. Then we have a borderline case. I leave a gap here because I will give a name to these cases. The borderline case is rs squared force is equal to rq squared. Then I have one degenerate horizon. Yeah, it's actually two horizons which they come together. Yeah, they are double zero of the function f. And that's what one calls a degenerate horizon. And it's situated at r plus equal r minus, and we can read the value from this expression. If the expression under the root is 0, that's the case we are considering here, then this double solution is just rs half. Yeah, so we have a degenerate solution at half the position where in the Schwarzschild case the horizon was situated. And then we have a third case. We have if the charge term is dominating. So this is certainly not a very realistic assumption, but mathematically it's a possibility. Then this here is imaginary, so we have no real solutions of our quadratic, and this means we have no horizon. Okay, so what does it mean? We will discuss the position of the two horizons in case A in a minute, and we will see that the outer horizon is very similar to what we are used to from the Schwarzschild spacetime. So we still have a black hole. So this is referred to as a black hole case. This here we still have a black hole because we still have a horizon, but it's somewhat special, and it's referred to as an extremal black hole. Black hole. And here in this case, where we have no horizon, but still the singularity at r equals 0, that's what one calls the naked singularity case. And we will discuss, in particular, the first case now in some detail, and then I will make a few remarks about the other two cases so that you get an understanding what is meant by these words. Okay, so these are the three cases to be distinguished. And yeah, if we want to understand what exactly is going on at the horizons in the cases where they exist, then we will do the same thing which we did for the Schwarzschild and the Kottler case. We will do a continuation of the metric across the horizons. So we will match the parts on one side of the horizon with the parts on the other side with the help of appropriately introduced coordinates. And this will be something like generalized Eddington-Finkelstein coordinates. So we will do this now in some detail for the case 1. And then we will discuss actually where the differences, the qualitative differences are in comparison to the Schwarzschild case. Okay, I think I should use this space a little bit here. So for the time being, for the next 50 minutes or so, I will consider case 1. And what do we have to do? If we want to discuss what's going on at the horizon, we need the equations for the radial light-like geodesics. Yeah, that was always the key ingredient. So we consider radial light-like geodesics. Radial, or let me just write light rays. It's just another word for the same things. Radial light rays, so they are given by what equation? I can read it from this expression here. Radial means this term is gone, and light-like means I have the tangent vector on the light cone, so I have a 0 here, and then I have minus c squared 1 minus rs over r plus q squared r squared dt squared plus dr squared 1 minus rs over r plus rq squared over r squared. And this gives me a differential equation for the radial geodesics. It gives me dr by dt squared is, this comes to the other side, then it is plus c squared 1 minus rs over r plus rq over r squared. And I solve this for what? For c dt, say. And of course I get two solutions, one with a plus and one with a minus, because I consider a square root. And on the other side I have dr divided by 1 minus rsr plus rq squared over r squared. And well, in the Schwarzschild case, this was an elementary integral. We could do it easily by ourselves on the board. With this term, it's a little bit more complicated, but it is still an elementary integral. So you can express it in terms of log functions. And I will do this in a minute. So if I put integrals in front of this, and I denote this here by, this is our Tertus coordinate. So I denote this by r. Well, most people write r star, but I use r star for the radius of a star when I have an extended body. So I use a different symbol. In the Schwarzschild case, I called it r hat. So this is now the analog of the Tertus coordinate, which we have known from the other coordinate. And actually, this integral can be calculated. I don't do it on the board in this case, but I write down for you what it is. Can I squeeze this there? No, I think it's not enough space. Nice music. So I write here what r hat is. And we have to distinguish the three cases. Yeah. Oh, I wrote case 1 on top of it. Okay, then let me only write it for case 1 here. So for case 1. Oh, I write it for all cases, and then I specify again for case 1. So let me write it this way. Of course, it's always the same expression, but if you want to write it as a real function, then it's recommendable to distinguish the three cases, right? So you can write it in a way that it is real. The expressions which you write down are real for case 1. But then you have for case 3, you have complex numbers in a way that the total thing is again real. So you have something like I times something, and again I times something, and then it gives something real. But I think it's more convenient to break it up in a way that it's manifestly real in all 3 cases. And then you get R plus R plus. This is this horizon value here. R plus divided by R plus minus R minus. And the log. This always means natural logarithm. So let me write ln. R minus R plus minus R minus squared. I forgot a square here. R plus squared, and here R minus squared. R plus minus R minus ln. R minus R minus. So you see, this is an expression which becomes infinite at the horizons. Yeah? If I have R equal R plus, then this here becomes minus infinite. And if you have R equal R minus, then this becomes minus infinite. So what this new coordinate does is it shifts the horizon to infinity. Yeah? One to plus infinity, the other to minus infinity. And that's why it's called the Tertes coordinate. We already talked about Achilles and the Tertes. Okay, this is for case 1. So for the case that RS squared over 4 is bigger than RQ squared. So in this case, we really have real values for R plus and R minus. Then the borderline case, R plus RS logarithm of R minus RS half. So you see, in this case, the horizon is at RS half. And again, what the coordinate does, the new coordinate, is that it shifts the horizon to infinity. And there's another term here, minus 2 divided by R minus RS half. And this is for RS squared fourth is equal to RQ squared. I'm writing with my fingers. And the last one, this is for the naked singularity case. Then I have R plus RS half, logarithm of R squared minus RSR plus RQ squared, which in this case is positive everywhere when I have no horizon. So it's meaningful to write it under the log function, right? You must have something under the log which is not negative. 2 divided by RQ squared minus RS squared half times the arcus tangent of R minus RS half divided by RQ squared minus RS squared over 4. This is also I have a 2 here. Maybe it's a writing mistake, I'm not sure. I have a 2 definitely here on my notes, but it might be a 4. I check again. Okay, this is for the naked singularity case, smaller than RQ squared.
R in the numerator?
This term? RQ squared minus RS squared, yeah, either over 2 or over 4. I think it's correct. So from the dimensions, it's correct, right? Length squared minus length squared. Why are you worried? There are no horizons, so anyway, there are no R coordinates. So this we don't have problems with zeros in the denominator in the fourth case. Okay, up to this 2 or 4 here, I'm pretty sure that it is correct. Anyway, so we consider the first case first, and well, now we have the equations for radial light rays. So we have then simply plus minus ct. And I have an integration constant, so let me put it on the left-hand side. Let me write it this way. Oh no, wait a minute, let me write it this way. Yeah, with a bracket, with a bracket. So let's say this is our head. So this is the equation for the light rays, right? For a plus, then it is the outgoing ones, and with a minus, then it is the ingoing ones. And now we introduce Eddington-Finkelstein coordinates in the usual way. So we just modify our time coordinate in such a way that one of the two families is mapped onto straight lines. And I do this because I'm interested in black holes, not in white holes. I'm doing this for the ingoing case. And I get ingoing generalized Eddington-Finkelstein coordinates. So the Eddington-Finkelstein coordinates are T prime, R, theta, and phi. Nothing happens with C and phi. They are untouched. And C T prime is just chosen in such a way that for the lower sign, for the minus sign, this becomes an equation for straight lines. So I would do with a lower sign, then the T comes to the other side. So this is CT plus R, right? Plus R hat. So if minus CT is equal plus R, of course, or minus R, CT prime for the minus R, right? Minus R. So if plus CT is equal to R hat, these are the ingoing radial light rays. Then I have CT prime as minus R. No, what I meant, sorry, I do two steps in one. So this is a coordinate transformation. That's a coordinate transformation. Now I write down the radial light rays. So for the radial light rays, I get then CT prime is, what am I doing? No, it was correct. It was correct with a minus R here. CT prime is for the ingoing light rays. Plus CT is minus R hat. So these two terms cancel. So I have, and I have the integration constant T naught. So I have CT naught. This goes away, and then I have minus R. So that's the equation for ingoing. And for the outgoing, I get it with a factor 2. So for the outgoing one, I have minus CT is equal to R hat. So CT is another times plus R hat, so I get 2 times R hat. So this is CT, plus 2 times R hat minus R. So these are the outgoing ones. Okay, and now I can plot them first in a RT diagram and then in an RT prime diagram. Yeah?
One question, which dimension, so which unit has R? Is it meter or dimension?
That's the length. That's the length.
Because when there's a length.
Because it's under the log. You're worried about that?
And also outside it somehow doesn't fit with the unit.
I think, here with this here. What has happened here? Oops. Wait a minute. You're right. Cannot be this way. Oh my goodness, what have I here? So what I've written there is exactly what I have in my notes, but obviously it's not right. Yes, you're perfectly right. This cannot be true. So something I've messed up here. Well, if you are worried about a dimensionful thing under the logs, then you can just add an integration constant and write it in the way another constant times log of something, and then you can combine the two terms. So that wouldn't worry me. But this is definitely wrong. This is definitely wrong. That's a length. On the left-hand side, we have a length. That is a length. That is a length. But this is definitely not a length.
Case 2 should be also proper.
Case 2 is exactly the same thing. It's exactly the same thing. Yeah. This is definitely wrong. This is definitely wrong. I'm sorry. Case 1 is correct, right? I don't know what I've done here. Okay, but case 1 anyway is the thing which is interesting most, so we will concentrate largely on case 1 anyway, and I hope that this is correct. This looks reasonable. Okay, so that's the equation for light rays, and we will now plot these as we usually do. Well, first we begin with original coordinates, so I plot here CT, usual t coordinate, and here I have my r coordinate. So now we are considering case 1, so I have two horizons. Here somewhere is r plus, and here is r minus. Maybe I should have plotted the function f. That would be helpful. Here, so r plus and r minus are the zeros of this function f, right? So let me draw a plot here. So if I plot f of r, we know it has two zeros in case 1, r minus and r plus. And how is it behaving? You see, if r is equal to 0, then this term becomes dominant and it becomes actually infinite, so it comes down from infinity. And if r is infinite, then this and this goes away and it tends towards 1. So if I have 1 here, then this is the limit. And now you can easily guess what the function is doing. This is a second order polynomial. Yeah, it's equivalent to a second order polynomial. So it can have only one extremum. So it must be something like that here. So that's the behavior of the function f of r for case 1. For case 2, obviously we have a double zero. For case 2, it's something like that. And for case 3, it is something like that. Oops. Yeah, so that's our function f. And that's the moment we are in this case where we have a 0 r minus and a 0 r plus. Oops. And that's what I've indicated. It's the other way around, of course. The convention is that we call the bigger one r plus and the smaller one r minus, as I've written it here on this board. Okay, and now what are the light rays doing? Now we can plot the ingoing and outgoing light rays. I said already that for big R, the situation is very much the same as for Schwarzschild. And we know what for Schwarzschild happened. We have the ingoing and outgoing light rays like that. So they asymptotically approach this horizon. This horizon R plus has very similar properties as Schwarzschild horizon. Yeah? And when we think of the Schwarzschild case, we know then inside the horizon, the first family, which approaches infinity here, comes down, and the other family comes up. And in the case of Schwarzschild, this then just proceeded towards the singularity. Now we have a second horizon, r minus, and this means the thing must go asymptotically towards this horizon. And this here must go asymptotically towards this horizon. And we have something new. We have this inner region here. So we have a region 1, which is similar to the exterior Schwarzschild case. We have a region 2, which is similar to the interior Schwarzschild region, with the exception that it doesn't extend up to the singularity. And we have a completely new thing here, where we have light rays, obviously, going in this way. And now let's see if we orient the light cones. So outside, and here's the region 3. In this region 1, we orient our light cones in such a way that we say that is the future. Yeah? And now if we want to extend this, I do the Eddington-Finkelstein extension in a minute. We want to glue this light ray together with this light ray. And then you see this is the future. This is the future. Yeah? So between the two horizons, we have the situation that the time doesn't go from the bottom to the top, it goes from the right to the left, as it does inside the horizon of the Schwarzschild metric. So we have here a very similar situation as in the corresponding region of Schwarzschild. You cannot stand still as a particular radius coordinate. You have to move in the direction of decreasing r. And our interior, here again, now we follow this geodesic down to here, and then we want to glue it together with this one. So this is now the future-oriented geodesic. Wrong. It's here. Yeah? So this is glued together with this, so it continues in such a way that on this side we have the time-lag vectors. Yeah, you can check this easily. These are the time-lag ones. The question is which ones are the future ones and which one are the past ones. And if you glue them together, if you do the extension, then this looks like that. So if we do it for ingoing at a Finkelstein coordinate in order to construct a black hole, we have here R minus, here R plus, and now the ingoing light rays are just straight lines under 45 degrees. And the other ones are bent even stronger than they have been before, because now we have this factor 2 in front of the log. So we have, wait a minute, these are the outgoing ones, so it begins in this way. Then I am here, so I have to continue in this way. And then I have to continue in this way. So these are the outgoing ones. And the light cones are in such a way that they fit nicely together, here, here, and here. So that's our Reissner-Nordström black hole. So the new feature is this interior region, and this interior region is quite interesting. So you see, if you look at this interior region, that it brings in a completely new feature. What is the new feature? Remember in the Schwarzschild spacetime it was like that. Whenever you had crossed this horizon, the horizon R+, you were doomed. Yeah? You had to end up in the singularity within a finite time. We calculated the time. In a similar way, you can calculate the time in the Reissner-Nordström case, the maximum time which is possible to stand between R plus and R minus. So if you have crossed the plus horizon, you will arrive at the minus horizon in a finite proper time. You cannot avoid this. But then, in a certain way, you are free again, because in this region, you are not forced to move in the direction of decreasing R. Yeah, because look at the light cone. Okay, you can go in this direction if you want to do it. Yeah? You have the choice to fall into the singularity if you want to do it. But you also have the choice to go away from it. Yeah? So in a way, the Reissner-Nordström singularity is more benign than the Schwarzschild one. Yeah, it doesn't really suck you in with in an inevitable way. Okay, so much for the mathematical theory. But now, if you think more in terms of physics, then we would say, well, for realistic objects, the charge is very, very small in comparison to the mass term. This means this horizon is very close to the singularity. Yeah? So see what changes if you crank up the charge. If you have no charge, you have only the horizon at R+, and the region 2, this region here, extend down to the singularity. Now you crank up the charge. Then this horizon moves a little bit, it's now in a different position, and then a new horizon comes into the game. Yeah, and it comes out of the singularity. So for small charge, it is very close to the singularity. So this region here, for realistic bodies, is a very, very small region, small in terms of this radius. And now here the curvature becomes infinite, which means you are torn apart. But if this is small, then it means that the curvature is already very, very big here. So you are torn apart already here. That's the only difference. Yeah. You are not torn apart immediately at the singularity. You are torn apart at a little bit bigger radius. But in essence, for an extended object like ourselves that is jumping into a black hole, the consequences are more or less the same as for Schwarzschild. Yeah? You cross the horizon, you have a finite time until you reach this second horizon, and then the tidal forces become so big that you are torn apart. The interesting thing is if the charge is not so small, if you think of hypothetical objects, most astrophysicists believe that they don't exist, but they might exist, where a star really has a considerable net charge. So it is associated with an electric field around it. Yeah? Then this could be a region of a size where you can move around quite comfortably. And then you could be free to escape from the singularity, even if you have crossed the horizons. So there are horizons. This means if you have crossed R+, you can never go back to the region where you came from. If you have crossed R-, you can never go back to the region where you have come from. But you have an escape. You can go in this direction now. And this is a new feature which we will discuss a little bit further. So this brings another question into the game. So for the Schwarzschild case, all causal curves, time-like or light-like, which entered into the region 2, actually ended up in the singularity. So none of them really could go up to arbitrarily large times. Now we have these new causal curves which go up to t prime equal infinity. And the new question, which was not present in Schwarzschild, the new question is, can I extend the spacetime in this direction in a different way? So do I have the possibility to analytically extend the metric up there so that I escape into another world? So I cannot go back in the world where I've come from. So here are all my friends. I will never see them again. But maybe I can escape into another world, which is as nice as my old one, and I might meet new friends. That's a new possibility. And we will see if this is true. Actually, it is true. So we will see that these light-like geodesics and time-like geodesics, they are not complete in this coordinate picture. So I can glue another piece of space-time on top of this, and then I'm in a new world. And this is a new feature. But before I do this, I will address the question, what distinguishes the particles which end up in the singularity from other ones? So I said I have a choice to go to the singularity if I like to. And I also have the possibility to escape. And what I want to prove now is that the fact that if I'm freely falling, then actually I will never hit the singularity. So remember from Schwarzschild, also there, free fall motion was recommendable because at least it extended your lifetime as long as possible. Here it's recommendable because then you are sure that you escape. You are sure that you will not end up in the singularity. You really need a drive, a propulsion, in order to steer towards the singularity. You can do this, but if you don't do this, if you let yourself just freely float through space-time, you will escape from the singularity. And that's what I want to prove now. I'm not going to discuss the geodesics in detail in this space-time. Most other features, in particular in the exterior region, are very similar to Schwarzschild. So they are not very, very important new qualitative features. But the new qualitative feature is what's going on inside the region R. And that's what I want to prove, actually. That inside the region R, if I am in free motion, that I will not end up at the singularity. Actually, that I'm bounded away from the singularity. Oops. And then we talk a little bit about the possible extensions. Maybe I should say one or two words about the comparison to the Kotler case. Also in the Kotler case, we had two horizons, you remember? For a particular interval for lambda, namely if lambda is between 0 and this value which I call lambda c, the critical value. For lambdas in this interval, we also had two horizons, but they were of a different character. Here, the outer one is a black hole horizon. For an observer at big radii, this is a relevant horizon which shields the singularity from him. This is a black hole horizon. And then you have an inner one, which I will only be able to learn about if I really move inside the first horizon. In the Kotler case, I had another horizon at big radii. So if I crank up the cosmological constants, then a second horizon comes in from infinity. We call it a cosmological horizon because it has something to do with the cosmological constant. So in the Kotler case, we had the black hole horizon, and then another horizon which was at a big radius. And this just prevented us from going arbitrarily far away from the black hole. But apart from that, it was not very relevant. So this here is on the other side of the black hole horizon. So the situation is quite different. Another way of putting this is that here we have a region static, non-static, static. And in the Kotler case, we had non-static, static, non-static. It was just the other way around. So it's quite a different type of horizon here, or of combination of horizons.
Might I ask a question
Sure.
about the astrophysical relevance of this object? I mean, okay, we cannot approach, we will be torn apart near the second horizon. So for us it's not so relevant. But if we imagine that these objects exist and if some particles approach the second horizon, then we must observe in our universe the birth of some particles which are coming from another universes.
So the question was about the astrophysical relevance of the inner horizon. So if some particle is falling into the black hole, then it will be influenced by the inner horizon in some way. And if I understand correctly, the question was, do I have a chance as an outside observer to get any information about what's going on inside, even if I myself remain outside? Is it possible for an outside observer to get some information about what's going on inside, maybe by observing some particles falling in or whatever?
I meant the particles which are being born.
These ones which escape here,
which are coming
and then come into another universe. So I'm not living here. I'm living up there in this other universe. Okay, so can I realize that a particle comes out? Well, actually, for me, if I'm up there, it would not be a black hole; it would be a white hole. We'll talk about this in a minute. So can I realize that a particle comes out of a white hole? Can I distinguish this from other particles? In principle, it should be possible. Because this is just causality. It comes from my past and moves into my future. So I can really do experiments with these things. So in principle, it should be possible, I haven't thought about a particular kind of measurement or something like that, which I could do, but in principle, it could be possible,
So then we must have the white holes in our universe.
Well, one way out of where the remark was, it looks like we actually would have white holes in our universe. Well, if it is true that all charges of celestial bodies are so small that this region is really very, very small, so that this horizon is very close to the singularity, then maybe it is so close that this classical theory breaks down, that I would need a quantum theory in order to investigate what's going on these small distances. And actually we don't have a quantum theory of gravity, so we don't know in which way the horizon would then be influenced. And maybe then this whole concept of a particle escaping into another world, maybe it does no longer work if we have a quantum theory. Nobody knows this at present. For a classical theory it works, but it only works in this region 3, which according to everything we know is a very small region in astrophysical terms for all our objects. It's very close to the center of these hypothetical black holes.
Is it larger than Planck lens?
It depends on what numbers you plug in. You may cook up a hypothesis how big a charge could be for a supermassive black hole, and then you could estimate how big this what this R minus is, how big it is, and you could calculate how strong the curvature is at this horizon. So if it would be reasonable, there to assume that an object could survive beyond R minus and could come out unharmed into another world. So I have no particularly strong opinion about this. What I don't make any predictions about this. But it's open to speculation. And there's another thing, the black holes we are talking about at the moment are all non-rotating. The picture changes again if we introduce rotation, and actually in a more relevant way. So everybody agrees that the spin of black holes does play an important role. If the charge plays a role, if the cosmological constant plays a role, most people would say no. But the spin definitely plays a role. And we will talk, Friday I will begin with the Kerr metric, and then we will definitely see that the picture changes in another way. This will open up new kinds of escape. It would kind of escape not in the direction up in the diagram, but actually in a direction in this way. Because we have no longer a singularity which blocks the way in all directions. We have a ring singularity, but we are free to go through it. So we have a possibility to escape into the region r smaller than 0 in the Kerr metric. We'll talk about this. So spin changes the whole thing again, drastically. And that's probably more relevant than this here. So what did I want to do? I wanted to talk about geodesics. I wanted to demonstrate that if I'm in geodesic motion, in free fall, that then I will never hit the singularity. So in a sense, you might say, yeah, the Reisner-Nordström singularity is repulsive. That's the way in which it is often put, yeah? The whole thing, the black hole, is attractive in a way, yeah, in the sense that if you have crossed this horizon, then you have to move towards it. Yeah, in this sense, it is still attractive. But if you have crossed the inner horizon, then actually the black hole doesn't longer like you. Then it more or less has a tendency to repel you. Okay, so we need time like geodesics. And as I said, I will discuss only one aspect, only the aspect if I can reach the question, if I can reach the singularity. So I have this Lagrangian, okay, more or less everywhere, every time the same thing. I'd introduce this abbreviation f of r. Let me write this again. Yeah, this was a function in front of the dt squared. So I can, just to spare a little bit of time, I can write it in this way. So this is our Lagrangian. Then we have the constants of motion, which are c squared f of r t dot and L square r square phi dot. Everything very similar to what we had before. And now for time-like geodesics, we use a proper time parametrization, so we have to equate this to minus c squared f of r t dot squared plus r dot squared plus r squared phi dot squared. And the quantity I'm interested in is the r dot squared. Yeah?
Is it L squared?
This is L, sorry. This is L. Here is the square. Mm-hmm. Yeah, the L is defined just as a derivative of the Lagrangian with respect to phi dot, right? And that's what I calculated here. Okay, so I'm interested in the question of whether R plus can be actually, in the quantity R plus, R dot. And from this quantity, I want to read some information about the possibility to reach the singularity. So I want to solve for R dot squared. Then I get, this is on the other side with a minus c squared, f of r. Then this becomes plus, this becomes plus. And I have an f of r squared. And for t dot squared, I introduce this expression. T dot squared is e squared over c to the 4 f of r squared. And then I have this on the other side. So it gets I have minus r squared. I multiply with this f of r. And then I have phi dot squared. Phi dot squared is L squared over r to the 4. So this goes away. And I have minus, so this was r dot squared. It is minus, I think now I have to write it out because I need the expression. Oh no, I don't need this, sorry. Or do I? Let me see. In any case, I can combine these two terms. That's certainly correct. That's L squared over r squared times f of r. And then this here gives plus e squared over c squared. Okay, and now I assume that I am in region 3. Yeah? That's the region inside the inner horizon. In the region 3, I have f of r is bigger than 0. I hope I haven't erased the function f. Oh, I did. I had the plot of f. It was like that. Yeah, remember? And here's R minus. Here's R plus. So here's the region 3, here's the region 2, here's the region 1. So in the region 3, f of R is monotonically decreasing from infinity to 0. F of R monotonically decreasing from minus infinity to 0. Okay, now my constant of motion has some value, any value, positive of course. And then I see if this function now, this is positive, this is something positive. If this function now decreases from infinity to 0, then with a minus sign, this term must go through a value where it cancels the e squared over c squared. E squared over c squared is some positive real number. Now f of r runs from minus infinity to 0. So there must be a value where the right-hand side becomes 0. A finite value. Yeah? So r dot equal to 0 at some radius r. What does this mean? It means that our curve, our light-like geodesic, must have a turning point. Yeah, it comes in, it has cross horizon r minus, and then there must be a point where it turns back. Yeah, where r dot becomes 0, and then goes out again. This is already a strong indication that the particle does not go through to the singularity. But we can read this even more explicitly if we rearrange the terms a little bit. So now I have to see how I do this. Now I think I have to write out the f of r. Let me see. How do I do this? Just a second. Oops.
So yeah.
Hmm?
So the f of r monotonically decreasing.
Yeah.
I thought it's infinity, isn't it? Just the function that goes from infinity to 0.
Yeah.
But minus infinity?
Ah, nonsense, plus infinity, of course. Why did I think I said it correctly, I also showed it correctly in the diagram, but I just wrote a minus sign, which is complete nonsense, of course, sorry. So, of course, it goes down from plus infinity to 0. Okay, so how do I do this most conveniently? Dot squared c squared. Yes, I think I know. I have to rearrange the terms in such a way that I have some nice terms, positive terms on one side, and the interesting terms on the other side. So I write this in the following way. I have to write it out. There's no help. C squared, plus L squared over R squared. Now I have to remember what the F was. And the F was 1 minus Rs over R plus R squared over R squared. And then they have a term plus E squared, C squared. Okay, and now I multiply this out. So I have minus C squared plus C squared Rs over R minus C squared RQ squared over R squared. And I think the rest I can leave as it is, plus E squared over C squared. For the term with the L, I can write again f of r. I don't have to write this out. Okay, that's the same thing, right? So now I rearrange things in such a way that I write some positive terms on the left-hand side. This is certainly positive if I take it to the left-hand side. And this is certainly positive. Plus L squared, R squared, f of r. Yeah, because I'm in the region 3, and in the region 3, f of r is positive. Yeah? And what do I have on the left-hand side? On the left-hand side, I have E squared divided by C squared plus C squared RS divided by R minus C squared RQ squared divided by R squared. And because this is definitely positive, it's strictly positive, even because C squared is definitely not 0. Yeah, so it's even strictly positive. And this means that this thing here must be smaller than what I have on the other side. So I have E squared C squared plus C squared RS divided by R must be bigger than C squared RQ squared over R squared. And because my radius values are positive, I can multiply with R squared without violating the inequality. So I have E squared C squared times R squared plus C squared RSR must be bigger than C squared RQ squared. And now let's look. This clearly says that the particle can never reach R equals 0. Why is that? Let's assume the particle does approach R equals 0. Then this becomes arbitrarily small. Yeah? Because this goes to 0 and this goes to 0. But this is bounded. Yeah? If RQ is different from 0, it doesn't work for Schwarzschild. Yeah? For Schwarzschild, I have RQ equal to 0. Then this just gives me a trivial bound that something which is positive is bigger than 0. I knew this before. Yeah? But if this is not 0, if I have a finite RQ, if I really have a charged thing, then I have here a bound which is different from 0. And this means the left-hand side cannot approach R equals 0. It must be bounded away. This means for any particular time-like geodesic, the value of E is specified by which particular geodesic I'm considering. For any time-like geodesic, I have a bound. R is bounded away from R equals 0. And the bound is, it scales with a charge, with the square of the charge. So this implies this here is strictly bigger than 0, and this means R is bounded away from 0. So my Reissner-Nordström black hole doesn't allow me to approach the singularity arbitrarily closely. In free fall. Yeah, I used the geodesic equation. If you look at the diagram, which I have there on the board, then you see it's obvious from this picture that if you use a propulsion, if you have a rocket engine or something like that, then it is possible to reach a singularity. Because this here is a light ray, and with a propulsion you can stay arbitrarily close to a light ray. So you can move in this way, and then you end up in the singularity. But if you are in free fall, what will happen is you reach a minimum, and then you move out again. Yeah? You will never reach this horizon, R minus. You will stay inside the horizon, but you will move out again, outwards again. And we will then next discuss what happens at infinity, so to speak, in this coordinate diagram. So we will talk about the question how to extend the region 3 into the future. Okay, so this was his argument with the geodesic equation, which I found quite interesting, that actually you cannot reach the singularity in free motion. So now about the extension, the extendability of the space-time. We talked briefly about the extendability of the Schwarzschild space-time beyond the Eddington-Finkelstein thing. I briefly talked about Kruskal. Kruskal is a maximal extension. Maybe you remember this. Actually, I will recall the most important equations. And then we will discuss what are the new features of the maximal extension for the Reissner-Nordström case. Actually, in the Schwarzschild case, the maximal extension was physically not very relevant. I mentioned this several times, because towards the future, if you have a Schwarzschild black hole in Eddington-Finkelstein coordinates towards the future, you cannot extend it. You can only extend it towards the past, and then you get a white hole. And we don't believe in white holes. Okay, at least I do here. So this is physically not relevant. But here we have a new possibility to extend towards the future, and that's a new and interesting feature. So we call Kruskal coordinates for Schwarzschild. So this was the following. I think I don't have to write down the transformation again, but I gave you the transformation. I called these coordinates u and v. These Kruskal coordinates u and v, which allowed you to depict the maximal analytical extension of the Schwarzschild spacetime in one diagram, in one coordinate picture. So we had the black hole singularity here, r equals 0. And we had mirror symmetrically a white hole singularity here. And then we had a region 1 here, an exterior region very similar to the region 1 in the Reisner-Nordström case. We had another copy of the same thing here. We had a black hole. The interior of the black hole was the region 2 in the Kruskal case. And we had a time reflected copy here. I think I called this 4. This was the maximally extended Schwarzschild solution in Kruskal coordinates. And an important feature of this diagram is that light rays go under 45 degrees. Yeah, so you can read the causal structure directly from this picture. So the light cones are just like that, under 45 degrees. Here you can read the propagation along causal curves immediately from this diagram. Okay, and as I said, the Kruskal extension is physically probably not relevant. If you think of a star which is collapsing and then forming a black hole, only the region to the left of my arm is relevant. Yeah, my arm is something like the surface of the star. Yeah, it begins here, then collapses towards the singularity. And what you have to the right of my arm, that's the outside region for which this diagram is relevant. And all this rubbish to the left of my arm is completely irrelevant because it doesn't occur in nature if I have this collapsing star. Yeah? Well, I have no vacuum in this direction, so it's just mathematics. It's completely irrelevant, unless we believe in the existence of white holes in the universe. But it's different now in the Reisner-Nordström case. I will show in a minute, or rather tell you in a minute without working out the details very much. I will tell you that then I have the possibility to extend the whole thing towards the right, yeah, the upper right-hand corner. So I still may think of a collapsing star, but now I have the possibility to extend the outside region in a new way. So the extension, the analytic extension, in my view, is much, much more relevant for Reisner-Nordström than it is for Schwarzschild. But before doing this, I should switch to a slightly different representation. Namely, if I want to talk about extension, then it's difficult if the extension is to be glued to the picture at infinity in the diagram. Yeah? It's very difficult to draw pictures which really where relevant things are really at infinity. So what you usually do is you pull the infinity in this diagram to a finite distance. So you put a function over your coordinates which puts the infinite interval from minus infinity to plus infinity into a finite interval. There are several functions which do this. My favorite choice is the Arcus tangent. Yeah, it does this. It maps the whole real line onto the interval minus pi half, I think. Yeah? So what we do is we introduce new coordinates, say W1 and W2, which are just what they are doing is just that they pull everything into a finite region. And because this diagram has a nice feature of having light rays under 45 degrees, it would be stupid to perturb this. So we do not put the Arcus tangent on the function u and the function v, but rather on functions which are rotated by 45 degrees with respect to u and v. This means we do it with the function u plus v and the function u minus v. Yeah? So if this is a u and the v axis, then I have here a u, what is this? This is u minus v, right? And this is u plus v. We have the axis under 45 degrees. And if I put the Arcus tangent on top of that, then I have these coordinates. So let's say this is u minus v, and this is u plus v. And then I get the whole picture into a finite interval, and that's what one calls a Penrose diagram. A Penrose diagram is, well, in an easy way, it only works for spherically symmetric spacetimes. It is, what it does is it pulls the infinity to a finite distance. So everything is within a compact region in the coordinate patch. And light rays go under 45 degrees. The radial light rays go under 45 degrees. So for the Schwarzschild spacetime, the maximally extended Schwarzschild spacetime, you do this by exactly this coordinate transformation, which I've written there. So the W1 and the W2 are the coordinates which give you the Penrose diagram of Schwarzschild spacetime. Some people say Carter-Penrose diagram. I'm not sure if this is historically justified. I have to check this. So until, I don't know, 5 years ago or so, everybody said Penrose diagram. And then some people claim that actually one should credit Brendan Carter. So I'm not sure if this is true, but I'm used to the term Penrose diagram since many years, so I think I will stick to it. So the Penrose diagram is a kind of compactification of this diagram. And we will then do a similar compactification for the Reissner-Nordström case. I will not write down the equations. They are a little bit clumsy. Well, not really difficult, but a bit awkward. So I will just tell you in terms of pictures what comes out. Okay, and then so what we call the Penrose diagram. I think this is spelled only with an N. Penrose diagram for maximal extended Schwarzschild. Looks like that. You have here the two horizons. Oops. Here the two singularities. And then you have the boundary. So this is a singularity. R equals 0. That's a black hole singularity. Oops. It should be symmetric, of course. It's not very nicely done. So and this should go through the corner at the horizon. Okay, I think it gives you the general idea. Of course, I will have a nice version in the written lecture notes. Here I have my white hole. Here I have several copies of R equal infinity. So this has now been been R equal infinity. This has now been moved into a finite distance. Here I have the horizon, which is R equal Rs in Schwarzschild case. Yeah. You understand how this is meant, right? The Schwarzschild coordinates where the R occurs doesn't cover the whole thing. So I have one version where the R coordinate approaches Rs here and infinity there. Then I have another version where an R coordinate approaches R equal Rs here and R equal infinity here. Yeah, it's not the same R coordinate system. This doesn't cover the whole thing, of course. So that's how it is meant. So that's for Schwarzschild. And you see, if you are in the outside region, well, you have not much choice. Either you stay in this region, this was 1, this was 1 prime, this was 2, and this was 4. So from 1, you could either stay in 1 for the rest of your life. That's what all of us are doing. Yeah, we are all staying in the region 1. But you have, in principle, the possibility to move into the region 2. And then to die at the singularity. That's the only possibility you have. You have no chance to move to this region. You have no chance to move to this region. And now let's look at the Penrose diagram for Reissner-Nordström. In this case where we have two horizons, I'm only talking about this case 1 at the moment. So Penrose diagram for maximal. Yeah, I will touch upon the question what actually the maximal thing is. Maximally extended Weißer Nordström. Okay, so we have a region 1. I emphasize this is very similar to what we know from Schwarzschild. So we have something like r equal infinity here, r equal infinity here. We have a horizon which is now at r equal r plus. Yeah? And we have a horizon here. So actually this was the horizon which I was talking about. If I do an extension with ingoing Eddington-Finkelstein coordinates, yeah? If I really consider a black hole, then I move in this direction. If I consider an extension with outgoing Eddington-Finkelstein coordinates, I construct a white hole and go into this direction. And then we got this new region. We got another region, which is different from what we have here. Namely, it extends up to another horizon, r equal r minus. Yeah? That's a region 1. I just erased the space-time diagram. I had the region 1, which was glued to a region 2 at the horizon r plus. And then I had an inner horizon where I have another thing coming. Yeah. And this other extension, which comes here, oh, I need more space, I see. That's bad. I'll do it again, sorry. the interesting thing happens here in the direction up there. I think I have to do it a little bit smaller. Hope you can still read everything. Let me try doing it like that. So this is a region 1. Then I have the region 2, and then I have a region 3, and the region 3 has a singularity, and the singularity is in such a way that freely falling particles necessarily evade it. So you see it has a different character from this here. Here every particle, freely falling or accelerated, had to end up in the singularity, and this means it has to be situated in this direction. So it is what we call space-like. Yeah? A space-like singularity is somewhere every observer, if he comes close to it, then he has to hit it. Here we have a singularity which can be evaded by some time-like curves, and this means it must be a time-like singularity. Yeah? Because it must open the possibility for some particles to pass by. So this is our region 3 in this case, which we didn't have in the Schwarzschild case. And now you see, you can glue here something. Well, no, here's infinity. Sorry, here's infinity. You cannot glue anything here. But here you could glue here something. You could do a white hole extension, you would get something like 2 prime here. Another version of this space-time, actually a time-reversed version, where you would receive signals from. So it would be like this white hole extension here. And but the new feature, and that's a really intriguing feature, is that you have something here now. You have another region. We have another region 3 prime here, and you have something here which is a new region 2. And you see, if you answer region 3, we have discussed that you can avoid the singularity. You can end up in the singularity. You see, the light rays are under 45 degrees. So there are causal curves which end up at the singularity. But there are also causal curves which enter into a region 2. And the region 2 is one where I am forced to move in a particular direction, right? And now I would be forced to move into this direction here, and would end up in direction h prime. And this is similar to the outside world. So here, in this region, I could move around in exactly the same way as in the region 1 I started with. Yeah? So this is our world outside of a black hole horizon. Then I enter into the region between the 2 horizons, cross the second horizon, be careful not to steer towards the singularity, go into this region 2, where I'm forced to move towards the region 1 prime. Here I cannot stand still at a particular r coordinate, and I end up in an asymptotically flat region of space-time, which is quite similar to the one I've started with. It's not the same. So all my friends are here. Now I am here. Yeah? But it is, as far as the space-time geometry is concerned, it looks exactly the same way as the space-time I started from. And you can extend this towards the past and towards the future as far as you like. So you can have infinitely many space-times. So here you may have an A double prime. Here you may have I don't know, triple prime, and so on. Here you have again singularities. And yeah, the singularity, that's another interesting aspect. When we started with the construction, we said it's a black hole. Yeah, we did the Finkelstein extension. We started in the exterior region. We mapped the ingoing light rays onto straight lines. So we really moved towards the future when we approached our interior part. And so we would say this is a black hole. I can cross the horizon from here to here, but not the other way around. I can cross it from here to here, but not the other way around. But now I am in the region 3. Now I discover this new horizon, which in the old diagram was at the top, at t prime equal infinity. Yeah, up there. So I have now the possibility to move into this direction. And an observer who's living here or here, he would say, this is a white hole. Yeah? Because everything comes out of it. Yeah, it's very much similar to this situation here. It's absolutely not similar to this situation. So for the observer here, this is a white hole. So we see, if we believe in this, extension business, then for a Reissner-Nordström object, it doesn't make sense to say it's a black hole or a white hole. It's always both. For some observers, it's a white hole. For some observers, it's a black hole. And this is the construction. So this is infinitely long. You can extend it infinitely far into the past and into the future. You always have here the singularities. Yeah, if this has anything to do with our nature, that's the question. We have already partly discussed it. Yeah, it's a question of how far we can trust this whole mathematical theory if we are very close to r equals 0. Yeah? If then a classical theory really doesn't give us a true idea of what's going on, or if we have to replace it by something else. Probably the question is in the second direction, and then all this is just mathematics. Then all this has nothing to do with the universe, just a second, unless we find stars which are really strongly charged, which have really a strong charge, then it would be different. That was the question?
So the general relativity is supposed to have the Planck length.
Certainly not beyond Planck's length. Let's put it this way.
So we can then estimate what the charge is.
Yeah, you can plug in numbers. You can see if you give me the mass of the stars, then you can calculate the charge, which would still give something which is which would still give a region 3, which is big enough for you to survive inside without coming too close to the singularity.
Not for me, but I mean for the particles. Like
for particles, yes. Yeah, okay. That's a different question. We don't really have to send our friends there or going there ourselves. We could just observe particles coming out from this region. Yeah, that's true. Yeah, we could look for particles coming out of white holes. Yes. Okay. Yeah, some people take this seriously, but of course, there's no indication until now from observations that white holes really exist. But this gives a mathematical construction which, in principle, would be testable. Yes, that's true. Okay, so I have 5 minutes left. Maybe I should say a few sentences about the other two cases. So we talked about the case where we have two horizons. Then we have the extremal case. The extremal case is, it's a kind of limiting case of this here where the two horizons come together, which means in this diagram the region 2 vanishes. Yeah? But let me just draw the case 2. Let me just draw the Eddington-Finkelstein diagram, or the RCT diagram to begin with. Then I have here R equal, it was R as half, right? In this case we have this double horizon, and we have outside the same situation which we are used to from Schwarzschild. But now inside we have the region where the horizons, where the light cones are still oriented like here in the outside region. So it's something like that, but the light cone is here. Yeah? See the difference to the Schwarzschild case. In the Schwarzschild case, the diagram looked similar. We had one horizon, but the light cone was here. Yeah? Now it is here. So the space-time is static everywhere, and the two static regions are separated by a degenerate horizon. So this would be the situation for case 2. And if you have the case 3, then actually the horizons are gone. There's no horizon. This means you come in from infinity. You reach the singularity at a finite value. And here it goes like that. So you have, let me draw 2 or 3 light cones. You see the light cone is always here. So space-time is static. No horizon, but still the singularity at r equals 0. We always have the singularity at r equals 0. This means if I'm observer here, I can see the singularity. Yeah? And that's why it's called a naked singularity. And this is an extremal black hole. A black hole where I have 2 horizons, but the 2 horizons come together. So these are the 2 other cases, which are, well, we have discussed the possibility a little bit if the Reissner-Nordström metric for the case 1 has something to do with nature. Well, as far as case 3 is concerned, I think the opinion is even stronger that it has nothing to do with what exists in the nature. So naked singularities are not very much liked. There's something which is called the Penrose conjecture. Maybe you have heard about it. It is a conjecture by Penrose, which goes under the name cosmic censorship conjecture. Cosmic censorship means, that's the conjecture, that nature is working in a way that it prohibits naked singularities. Yeah? So there's a censor at work who makes sure that naked singularities are not formed. Yeah? So if a star wants to collapse, then the censor makes sure that it will collapse to a black hole with a horizon and not to a naked singularity. There are some theorems which go in this direction, but nothing which could be really called a proof of the conjecture in the sense that it would really state that under all reasonable assumptions which we would like to be satisfied, a naked singularity is not formed. There are some assumptions always to be put in which some people might call questionable. So typical assumptions are energy conditions, that energies are not negative, that energy is not moving with subluminal velocity or something like that, with superluminal velocity. Most people would accept this. But one also needs additional assumptions which maybe are not so clear. So most people believe that naked singularities do not exist, but we cannot be really sure. Okay, time is out. I think that's what I wanted to say to the Reissner-Nordström case. And then on Friday we will finally begin with the Kerr metric, which actually I had planned to do already a little bit earlier, but we will have time enough to discuss Kerr in some detail. Okay, see you on Friday.